So welcome everybody to today's IAMP One World Mathematical Physics seminar. It's a great pleasure to have Michael Loss as a speaker today. And Michael will tell us about which magnetic fields support a zero mode. So let me say that as usual, the seminar will be recorded and it will be made available on YouTube. So Michael, I leave the floor to you and thank you very much for being with us today.
Yeah. Thank you very much, Marcello. It's great pleasure to give a seminar here. And so the title you have seen, and this is somehow an old problem. I mean, really old. And fortunately, I got Rupert Frank involved, and he had a lot of enthusiasm. And in some sense, most of the ideas are Rupert's, which I'm going to tell you now. So before I get into zero modes, I would like to tell you a little bit about remembrance of things past, right? So the story is, if you'll take a hydrogenic atom in a magnetic field, hydrogenic I mean because it would like to have the charge number variable, then you know it's the usual minimal coupling, right? Minus I grad minus A squared minus Z over X, and the magnetic field, of course, is given by the curl of A. And if you are interested in the ground state energy, there's a wonderful inequality, namely Kato's diamagnetic inequality, which I've written down here at the bottom. And what this diamagnetic inequality does for you is it tells you that the ground state energy of the hydrogen with a magnetic field can always be bounded below by the ground state energy of the hydrogen atom without the magnetic field. This is what we usually call diamagnetism. Yeah. Now, what of course happens when you have a magnetic field, you have to think that electrons carry spin, and then the story changes quite a bit in the sense that you pick up an additional term minus sigma dot B, right? An interaction of the magnetic field with the spin. And so here's the notation. I call psi a spinor, right? Has two components, psi 1 and psi 2. They are both complex valued functions, and we normalize them so that the sum of the modulus squared adds up to 1 of the integral. And B is the curl of A, and sigma dot B is this somewhat complicated matrix here. And you see the story here is then very different from what we had before, namely the sigma dot B term can really lower the energy dramatically. And you can easily convince yourself that you can cook up even a constant magnetic field. Already tells you that when you let the magnetic field go off to infinity, that the ground state energy of this Hamiltonian tends to minus infinity. Okay, so by the way, this Hamiltonian is of course gauge invariant, so really the energy depends only on the magnetic field and not on the vector potential. Yeah, this is, by the way, what we call, I think, paramagnetism. Okay, so now let me sort of tell you a little bit how one gets into the zero mode business. Namely, what you think is, okay, the electronic energy goes towards minus infinity, but of course, if the magnetic field gets very large, in some sense, you have to pay a price, right, to the power company. And the price you usually pay is you add onto it the field energy. And in my units, I used atomic units. It looks a little bit weird. You get 1 over 8 pi alpha squared, where alpha is the fine structure constant. And you can actually write the functional, which is associated with this Hamiltonian here, in this fashion, as I said it here, sigma dot minus I grad minus A psi, and the modulus squared, the L2 norm squared. And this is a wonderful formula. When you work out the square of this operator here, you see my pointer, it turns out to be precisely that expression here. So that's an old formula, but it's good to be reminded of, okay? And so then the question came up, what I think in 1986 or 1985, this isn't 35 years ago, well, when you take now the infimum of the electronic energy plus the field energy, well, is this bounded below? Okay, right? So, well, is it? And it turns out there is an obstruction to that. And the obstruction is zero modes. So I've written down what is a zero mode. It's sigma dot minus gradient minus A psi is equals 0. Okay, So psi must be a normalizable spinor. That's important. The sigmas are, of course, the Pauli matrices. I wrote it out here again for your convenience. And you see this sigma dot minus I grad minus A operator looks rather complicated. They've written it out in matrix version, right? Another thing which is also important is it's often quite easy to find zero modes when you let the A to be crazy, say grow at infinity, and the B crazy. But you really would like to have that the magnetic field, say, should be in L2. All right, finite energy. So now you see, if you have such a zero mode, suppose you have one, then what you can do is you can just rescale the A field, and you can rescale your psi. It still is a zero mode. And what you have done when you go back to the energy functional, you have killed in some sense the kinetic energy part. It's not there anymore. And all you're left with is the potential energy, the Coulomb energy, and the field energy. And when you undo the scaling, you pull out the factor of lambda. And now you see, when you choose the Z large enough, you get this number to be negative, and therefore you drive this whole problem to minus infinity. So there was, I think, a theorem, a nice theorem, I think, by Jörg Fröhlich, Elliot Lieben, myself in 1986, namely that the hydrogen atom is unstable if and only if there's a zero mode. And so then comes the question, well, are there any? And you see, these are zero modes in 3 dimensions. They're not sort of governed by any index theorems or anything of that kind. And so remember, zero mode means what? The psi should be square integrable, and the field energy should be finite, or at least the magnetic field should be confined. Okay, so are there any? And it turns out there are. Hongzhou Yao and myself, we found these zero modes in 1986, and you can write them out explicitly. So here's the psi. It's the identity plus I sigma dot x divided by this factor, and phi is a constant spinor, right? So this is a nice function. You see easily it's square integrable. And then you also can write down the A, which has this funny form, a 3. I mean, the numbers must be there. I mean, there's no way around it otherwise. A 1 plus x squared squared. And then you have this funny expression here. So this is the cross product of w with x, w dot x times x, and then 1 minus x squared w. And the w, or omega, I think it's w, is you have to relate it, of course, to psi. And the way you relate it is that you set w equals phi, sigma phi. So this is a vector, okay? And by the way, this bracket here denotes just the inner product on C2, okay? It's, by the way, funny. So this pair, psi and A, really is a zero mode. And it's funny that this A actually turns out that the field lines of A, when you pull them back from the Hopf vibration, when you pull back the Hopf vibration from S3 to R3, these are precisely the field lines of A. The magnetic field turns out when you calculate the curl, you get a factor of 12 up here. You get here a power 4, but this term is exactly the same. And so this is easily seen to be square integrable. It's actually very nice. So these are examples. And of course, many, many more examples sort of were found of zero modes. This sort of generated an industry. Now, I would like to address the question, well, you know, how big in some sense does a magnetic field have to be that it actually supports a zero mode? And for that, I would like to go back to, and this sort of governs what's going on, to explain the Sobolev inequality. So we think of the function f, a function from Rd into the complex numbers maybe, or real numbers. And Sobolev's inequality says there is that the gradient, the integral of the gradient of f squared is bounded below by a fixed constant s, it's written out here, times the p norm of f to the squared. And the p is a very specific exponent. It's 2d over d minus 2. And that's, of course, because you want to have that both sides have the same dimension. Okay. It turns out this constant is sharp, and this equality if and only if up to translations f is given by this function here. And this has been figured out, interestingly enough, by Rodemich already in 1966. He gave a seminar at Caltech about this. And then, of course, Talenti, 76, and Aubin. So this is an inequality which we sort of going to use now in the talk. And I would like sort of to simply state the facts here. Okay. So now let's go back to a simple problem. Suppose you would like to figure out what is the measure on the potential supporting a bound state with negative energy. And we just take a minus Laplacian minus v. V should be positive. Very nice, goes to 0 at infinity. And if one seeks a measure of this potential in terms of LP norm, in an LP norm, then the only possibility is that you have to take the 3/2 norm. And that's clear because if you assume that you have to assume that these two terms have the same dimension. So the scaling is that the potential scales like lambda squared v of lambda x. And the only norm which is scale invariant is this one. Okay, so then how do you argue? Well, you take the energy, right, which is given by this difference here. And then the first term you estimate by the Sobolev inequality, right? That's the previous inequality here. P, by the way, in 3 dimensions is 6, right? 6 divided by 1. So here it is. And then you do a Hölder inequality on this term, you get the 3/2 norm of v times the 6 norm of f squared. So you get this term, and you see obviously a necessary condition for a bound state is that the 3/2 norm of v is bigger than S3. And so this condition is sharp. So when you are less or equal, it's not going to work. When you're strictly bigger, it's going to work. And this is a well-known result, right? It's ancient. So that brings you to the idea that you can apply a similar argument to the zero mode problem, right? What you do is you take the zero mode equation, you square the operator, that's this one, and then you say, well, I take the kinetic energy, that's this term now, which is equals to b dot psi sigma psi of x dx. You do a Hölder inequality, and you realize that the length of the spin psi sigma psi is exactly the magnitude of psi. There should be a square here. The square root is wrong. And then what you do is, again, you use the diamagnetic inequality, which tells you that you can estimate this below by the gradient of the modulus of psi. And then you're back exactly to the case which I just discussed before, namely the magnetic field 3/2 norm should be bigger than S3. That's certainly a necessary condition for a zero mode. Of course, I mean, this is clearly extremely crude, right? I mean, this is not going to give you any decent result. And what Rupert and I tried to do was to improve on that. Okay, so here are some preliminaries. So you can always assume that the A potential is in L3, right? I mean, because the B is L's 3/2, and then you can write the A potential, one version of it, by this expression. It satisfies curl A equals B and divergence A equals 0. And you can easily check using the Hardy-Littlewood-Sobolev inequality that this A potential is in L3. Here's an interesting theorem about the solutions. If you have any zero mode solution in LP, for some P strictly bigger than 3/2, then you know with this assumption that the A is in L3, that the psi is actually in LR for any R strictly less than infinity and strictly bigger than 3/2. This is some sort of regularity which is useful to have. By the way, you cannot in general reach L infinity. There's no theorem of that sort. It's like that. It's kind of a Moser iteration which sort of breaks down and doesn't give you the infinity case. It's very similar, analogous to the results of Bresis and Kato about the Schrödinger equation. So anyway, so here is then an improvement. So we talk about a zero mode solution, right? So the A is in L3, the B of curl is in L3/2, we have sigma dot minus I grad minus A psi equals 0. And that's the theorem. So B is a magnetic field with diff B equals 0. A necessary condition for this equation to hold, to have a weak solution in LP for some P bigger than 3/2 is that the 3/2 norm is greater or equals twice the Sobolev constant. So it's, I mean, you might say it's laughable, right? So you have an improvement from 1 times the Sobolev constant to twice the Sobolev constant. But you see, these are somehow tricky problems. I mean, if you really want to see how tricky these problems are, you should have a look at this paper of Cosetti, Vanelli, and Krejcik, where they talk about absence of eigenvalues for the Pauli operator. And this is really a very difficult problem. I mean, our approach is actually much, much simpler in a way. I mean, they don't have that result, right? They look at a different aspect of this. Okay, so my point here is I would like to explain to you a little bit how you get to this result, how you get to this factor of 2. And the deal here is that you need a new kind of diamagnetic inequality, right? So the old one, I mean old, Katos, is actually quite an elementary observation, right? You write your psi as the modulus of psi times the phase. You work out what this gradient square is. I mean, this left-hand side, and you see it's obvious, right? But still, it's a powerful inequality. For example, it tells you that the Green's function with a magnetic field is bounded above pointwise by the Green's function without the magnetic field. So it's definitely an interesting inequality, but it's not sufficient for us. So we're going to go out now. Here's a lemma. And this lemma says, if you have a 0 mode, right? Sigma dot minus I grad minus A psi equals 0. And psi is in LP for some P bigger than 3/2. Then we know that psi is in H1. And the modulus of psi is also in H1. And moreover, almost everywhere in R3, you have a pointwise inequality, namely that the gradient of the modulus of psi squared is now, which of course is certainly less than this thing here, but now you have also a factor of 2/3 in front. And that I would like to explain to you. And this has to do with an algebraic fact. And there you have to really use the spinor structure. This is not something which you have, I mean, the spinor is really important, right? I mean, clearly you have to use the 0 mode equation. That will come out. These are ideas actually which have been worked out by Calderbank, Goduschan, and Herzlich around 2000, also by Feehan in 2001. And these are inequalities which also were used by Yau in his solution of the Calabi conjecture. It's in certain circles a well-known thing. And Rupert was somehow able to dig this up. So, okay, so how do we get to this factor of 2/3? So let me go up, start with an algebraic fact. So V is just a spinor. Forget about X, and it's just a spinor in C2. Beta is a vector in R3. And we look at the following operator. So you take beta tensor V. Pi is this operator here, defined it here. So what you do, you take the spinor, you multiply by this number, beta J. Then you take sigma dot beta, that's a matrix, you apply it to the spinor. And then you multiply that matrix by one of the Pauli matrix, sigma J, and put the factor 1/3 in front. What you easily can check is that when you multiply this gadget here by sigma J, so you have a sigma J, beta J, and you sum on J, then you get 0. And the reason is, of course, that you get here sigma dot BV, but here you get the sigma J squared, which is 1, and summing that gives you a factor of 3 that cancels out, right? So this is a fact. Now, what we do is on this space, we introduce an inner product, beta tensor V, gamma tensor W, to be the sum beta J, gamma J, and here, of course, V and W is just the standard inner product of spinors, okay? You can easily check that this pi, this operator, which is some kind of a projection, if you like, is symmetric. So in other words, when you have the pi on beta tensor V, comma gamma tensor W, you can move it over onto the other side. And when you compute the length of this projection squared, so in other words, you see, this is of course a spinor, right? So what you do is you take the inner product of this guy with itself in spinor space, and then you sum on J. And when you work this out, you get 2/3 the length of beta squared, length of spinor squared. And so here you see, this is the factor of 2/3. Okay, so now what does this buy us, right? So this is an algebraic fact. It's very easy to check. But of course, the problem is how you come up with this. And that's what these people did. It's also, by the way, related to what is called the Penrose Projector, although I don't really understand much about that. Okay, so how do we use that? So it's just differentiation of Sobolev functions. So what you do is you do the usual thing, you regularize the problem, right? When you differentiate the modulus of a function, you have always a problem where it vanishes. So you add a little epsilon squared and take the square root. And then you take the derivative, right? So here's a very simple calculation. The partial of psi epsilon, you can write in terms of this real part, psi over psi epsilon dj psi. And you see, since you take the real part, you're for free, stick in the minus IAJ. Notice I don't have an I in front of derivative. I stuck it over to the vector potential. Okay, so that's clear. And then using this, you can easily check that when you take the modulus, so in other words, the modulus of this vector, which you can write in this fashion, right? You learn that this is the real part of this somewhat complicated expression, right? You have psi divided by the modulus of psi, grad modulus of psi over its length, and grad minus I a psi. All right. So, and now comes the point. This second factor here, you can write in this fashion. You see here, this is precisely the pi on the gradient minus IA psi, the jth component. And why can I do that? Because we assume that the psi satisfies the zero mode equation. So this term disappears. It's just not there. It's zero. So you gain in some sense, but because the zero mode equation allows you to stick in a pi at this point. So you get this formula here. Okay. Good. And from then on, it's actually a simple matter what you do, right? I wrote it out here once more, right? You move the pi over because it's self-adjoint on the other side. And then you use the Schwarz inequality. That's what I've done here. And then you notice here that this is a unit spinor. This is a unit vector. And so you get right away that you use this fact here, right? What I had before. And what you learned right away is that this whole factor here is square root of 2/3. I mean, when you square it, in other words, you get precisely this estimate. Okay? So this is the first step here, right? This is a kind of new diamagnetic inequality, and what it buys you because you have a zero mode, a factor of 2/3 in front. But this is not the whole story. So you see, in some sense, Rupert and I will suspect that these zero modes, which Yao and I found, they are presumably the optimizers for an optimal magnetic field B. Now let's look at this. If you take this spinor psi and you take its magnitude, well, then you get 1 over 1 plus x squared. Now, when you take the square root, then you notice that this function is precisely an optimizer of the Sobolev inequality, right? Let me maybe go back to remind you. The Sobolev inequality, I had it here, right? This is an optimizer. You see, any lambda will do, right? Okay. And in 3 dimensions, the exponent is d minus 2 over 2. That's 1/2. So this is a Sobolev optimizer. Okay. So that suggests you that you should do some work with this function, right? And by the way, when you use these zero modes of Yau and myself, it turns out that the magnetic field, which we suspect is the optimal one, when you compute the 3/2 norm, you get 4 times S3, where S3 is the optimal Sobolev constant. So we are still off with our result of Rupert and mine by a factor of 2. So then what should we do? All right, so now from now on, we will concentrate on the modulus of psi to the power 1/2. Here's a lemma. So we do again, the psi is in H1, the epsilon is positive. Then this is a function which is weakly differentiable. The gradient is in L2. And almost everywhere we have in the sense of L1. So in other words, all these terms here are integrable, the following formula. So look, I'm not going to check it for you. It's an easy, once you know what the formula should be, what you're looking for, it's relatively easy to check. And you notice this formula is kind of nice because yes, there's a factor of 2 and this has a factor of 3. And you see the 2/3 says is showing up here. Okay. So the proof of this formula is very straightforward, but there's an additional advantage here because it's very easy to stick in the A field. In fact, you can actually immediately write down the formula in this fashion. When you stick in the A field here, you see that these A fields all nicely cancel out when you really do it in the right way. Now you see I have a factor of 2. Here's a 1/4. That's the 1/2. Here's the 1/2. It works out perfectly. Okay. And now you see what we do. Remember, the psi modulus epsilon is just squared. It's just the modulus of psi squared plus epsilon squared. So you really arrange this gadget here in the following way. You write it as this 1/2 thing here, minus 1/4 psi epsilon, this term here. There's no epsilon anymore. And then you have some adjunct term, which is proportional to epsilon squared. But you understand at the end, you let epsilon go to 0, so this will disappear. But notice you get this term, and this term we know is positive. And therefore we have an estimate, namely the gradient of this 1/2 power squared is less than this right-hand side. It's very simple. Okay, next what you do, you integrate, right? I've just done this here. Now, integrate this term over by parts. So you get this gradient minus IA squared on psi. There's some minus signs here. Use the zero mode equation, you get the B. You now do a little bit of Schwarz inequality. You get this 1/2 B of x psi squared over psi epsilon dx. And then at the end of the day, let the epsilon go to 0, and you have this wonderful inequality. And you see right away now, on the left side, you use Sobolev's inequality, right? But you see you have the psi to the power 1/2. That gives you the 3 norm. And on the right-hand side, you use Hölder's inequality with the 3/2 norm on the 3 norm. And sure enough, you get the result that the B 3/2 norm has to be bigger than twice S3. So this is the proof, essentially. Okay, great. So now comes the question, well, how good is it? And now things getting to be weird. Let's look at the following problem. What I'm doing is I'm considering a monopole field. So G is X, the curl of A is the magnetic field, is X divided by R cubed. R is the modulus of X. And it's well known when you, for example, choose the string on which the A, I mean, you cannot have, you see, the divergence of this gadget is not 0, right? I mean, curl of A is not really a legitimate thing to say because it's singular. But what you can definitely do is if you allow for a certain singularity along a string, which I've chosen here to be the negative z-axis, you can actually write down an A field, the monopole A field, and this is the factor G. And now you do compute sigma dot A psi with this psi here. You get this expression here. You compute minus I sigma dot grad psi for this psi. You get this expression. And what you notice is these are exactly the same expression provided you choose G to be 1/2, which is, by the way, precisely Dirac's quantization condition, right? Okay, so choose the G equals 1/2, and what you have gotten is, if you like, a monopole zero mode. Of course, it's not really what we want, but what is most interesting is, so if you choose G equals 1/2, you have this equation. You compute this pointwise, you get 1/4 1 over x cubed. You compute this term pointwise, you get 1/4 1 over x cubed. So what this turns out is, in this inequality, if you forget about the integrals, you have essentially a pointwise inequality. Maybe I should, yeah, right. So in a way, if you look at this problem pointwise and you use monopoles, you haven't lost anything. And that bears out. I mean, you can look at all these inequalities which we use, and you can chase them through, and you see you get always cases of equality. The monopole field just nails it beautifully. Okay, so there seems to be really something which we miss on the one hand. On the other hand, we can get some additional results. All right, and so let me go back to Sobolev. So if you look at the Euler-Lagrange equation for the Sobolev constant, so that's minus Laplacian f minus f50 equals 0. So I chose the constant here in front equals 1. So you have a whole bunch of regular solutions. Up to translations, they're given in this fashion. Of course, yeah, right. What is interesting is, if you optimize this over lambda pointwise, you get x to the minus 1/2. And when you take 1 over square root of 2x to the minus 1/2, you have again a solution of the Sobolev equation. So this is a singular solution. But also this x to the minus 1/2 is an optimizer for hardness inequality. So this suggests that we can actually get a different kind of requirement on the magnetic field, which guarantees at least for some zero modes. Or no, not guarantees, but it's a necessary condition for zero modes. So let's see. How do we do that? Let me demonstrate this in the Sobolev case. You take the usual energy, right? Remember, you would like to find a condition on V so that this has a negative energy bound state. Okay, so what do you do? So this is negative. Well, you do the symmetric decreasing rearrangement. That lowers this term. You do the symmetric decreasing rearrangement on V and F. That increases this term, but you have a minus sign here that lowers this again. And then you do something interesting, namely you divide by x squared and multiply by x squared and pull out the supremum of this term. Okay. Now it turns out this number which you get has a name. Namely, it turns out that up to a factor, the weak L3/2 number of the potential is precisely given by that. And you see, since this is negative, by hardness inequality, you need as a necessary condition for this to be negative that this number is bigger than 1/4. Okay, so now we think there's a fair chance that we can get a similar fact also for the zero mode problem. And indeed, this is true. This is the theorem. Take the B to be in L3/2 weak, a magnetic field. Divergence B equals 0. If one has a weak solution, a non-zero solution, then necessarily the weak norm 3/2 must be bigger than this number. Or equivalently, the supremum over all x squared B star. So you take the modulus of B, you take its rearrangement, that's greater or equals 1/2. And interestingly enough, of course, the 1/2 x over x cubed, which is the monopole field, is an optimizer, I put this in quotation mark, which of course, the divergence of this gadget is not 0. So it's clear that in this circle of ideas, there's definitely a whole bunch of things which have to be understood, or at least we don't understand them yet. So that summarizes, in some sense, the story about the magnetic field. But what I would like to do is I would like to illustrate the method and a number of other in another problem. By the way, how am I doing with time?
I think you still have 20 minutes.
20 minutes. Oh, that's great. Okay, good. Yeah. Good. So here's another theorem which is, so suppose you look at the following spinor equation. So you assume the lambda is a function, real function in L3. and you look at this equation, minus I sigma dot grad psi equals 3 lambda x psi. So it's like a potential problem for minus I sigma dot grad, this operator, which is a first order operator. Now notice, by the way, the spectrum of this operator, you know, there is no sign, right? It goes from minus infinity to plus infinity. But still, you can make some statements which are quite analogous to the statement about the potential problem for the Schrödinger equation. Namely, it's the following. Suppose this thing has a weak solution, right? Psi in LP for some p between 3/2 and infinity. Then the 3 norm to the power 2/3 of this lambda is greater or equals this number. S3 is just the area of the three sphere in 4 dimension. You raise it to the 2/3 times 1/4. And interestingly enough, there is equality in 7 if lambda of x is 1/1 plus x squared. Now, which you remember, lambda of x equals 1/1 plus x squared is, sorry, let me go back. It turns out when you, let me go back a little bit. I should maybe have written this down here. When you take this spinor and you apply minus I sigma dot grad to it, you get precisely 3 times 1, 3 divided by 1 plus x squared times psi. So in other words, it's not only a necessary condition, but if you have equality, actually have an example. So this is sharp, right? And so now how does one prove something like this? Let me just sort of glance over the ideas. So you look at this equation, and again, you consider this projection, right? But now you twist it slightly differently. Namely, what you do is you look at pi of dj minus I lambda sigma j psi. Because you see, when you plug this in here, you see that you get the right-hand side, and since the psi's are solving this equation, what am I doing? Yeah, right. This is equals to 0. You can check that. It doesn't look like it, but it actually does, is 0. You see, why this is 0? Because the sigma dot sigma gives you sigma I squared, and you do sum it, that's a factor of 3. That's this 3 which you have here, okay? So this is 0. And again, you use this idea about the diamagnetic inequality, but in a different twist now, and you get the following inequality, namely that 3 times the gradient of the modulus of psi squared is less than twice this gadget here, okay? And then you proceed in the usual way, right? You look at an inequality for the modulus of psi to the power 1/2. So you work yourself through in a similar way as we did before. You get to this, and then you do Hölder inequality, and you see right away that this function saturates this inequality with this spinor. Yeah, here I wrote it, right? Okay, it's a simple computation. So now. You see, these things don't exist sort of in vacuum, right? The tricks are kind of strange here, which we use, but what is behind it is really some sort of differential geometry, in particular differential geometry on spin manifolds. Yeah, I should also say these results on the magnetic field, we figured out they work in any odd dimension. I think they also work in any dimension, greater or equals 2, except, or greater or equals 3, I should say. But we haven't bothered yet to work it all out in detail. The scalar equation, this one here, this works in any dimension, greater or equals 3. Actually, greater or equals 2, in fact. And let me now give you a little bit of a background how one can understand this. Well, understand it. I mean, I'm not expert in this field. So if you look at the Dirac operator on the D sphere, right, and the standard metric is called G, then what you do is in this business you conformally deform the metric. You multiply it by a factor, e to the 2u, and then the Dirac operator has a certain way of transforming. And this is how it does. In other words, you take the spinor, So there is a certain spin structure which you have on SD, and when you conformally change it, in principle you change the spin structure, but you really don't, because it's just a conformal factor. So the Dirac operator, what you have to do is you have to multiply first by this multiplier here, then apply the standard Dirac operator on SD, and then undo certain multipliers again. Okay, this is the way how the Dirac operator transforms. And there is a paper by Hijazi in 1991, and he is the one who really got this whole thing to work, who says that if you take the first eigenvalue of the Dirac operator, the first eigenvalue is not zero, but it comes in pairs, a -1 and a positive pair, right? It's the same absolute value. So the square is greater or equals d over 4d minus 1 times the first eigenvalue of what is known as the conformal Laplacian on SD. So L is the standard Laplacian on SD, and then you conformally change it by pre-multiplying with this multiplier and post-multiplying. Okay, so that's what he got. I mean, I'm not going to prove this. One can read this up in his paper. It's a CMP paper. So now with that, you can do a few things. Let me write out lambda 1 LU. What is it? It's the infimum over all functions. Now you have all these prefactors, right? But taking this into account with this conformal Laplacian, what you get, you can write this whole thing in this fashion. Okay. And then what Hijazi does is the bottom, he estimates by Hölder's inequality to get to this power. Okay. Then here you have the volume, but so the volume is the standard volume of the SD, but you have this prefactor e to the du, right? And therefore what you get is you get this lower bound that the first eigenvalue squared times this funny factor is bounded below by this quantity. I mean, it looks complicated, right? But the point is, if you choose, oh, I chose G, that's bad. But anyway, call this function e to the d minus 2 over 2u, f, call this G. Then what you see is that this whole mess turns out to be this expression. And this expression is well known to people who work on the Sobolev inequality, because when you pull the Sobolev inequality back onto the sphere, that's exactly the ratio for the Sobolev constant on the sphere, okay? And we know what the best constant is, namely, this whole expression is the infimum is given by this number, okay? This is the sharp Sobolev inequality. Okay, so you see what we then get is we get that the first eigenvalue of this conformally deformed Dirac operator squared times this funny factor is bounded below by a fixed constant, universal constant. Okay, so now what can we do with that? Let's do a crude thing. Let's look at this gadget here. So I invert the Dirac, right? So this gadget, right? And remember, you always have to integrate over the volume, is bounded above by 1 over the eigenvalue magnitude times this quantity, right? I mean, this is just a spectral estimate. And then you work out, you know already now how big this eigenvalue can possibly be, right? This is the previous result here, right, of Hijazi. And that's what you get. And now comes and since du is conformally deformed Dirac operator, you plug this in, right? And you happily do that. And you notice with this e to the du, and this guy with the minus happily conspires to give this factor here and give the same function over there. And you have a d minus 1, okay? D volume. And D volume is the standard volume on SD. All right, so the upshot of this is that this left side is less or equals than this right side. You have this funny factor here, and you have this L2 norm of phi squared against this factor, okay? So now what you do, you see, the U has not been determined yet. You can choose it in any way you like. And what you're going to do is you set e to the d plus 1 over 2u phi equals phi twiddle. And what you then get is that this quantity here with this phi twiddle, which is this one here now, is less than this constant times this quantity here, phi twiddle e to the minus u d volume. But you see, if you replace the e to the du in terms of phi twiddle, what you get is precisely this inequality, which I have on the top. All right. Okay, and now for d equals 3, since S3 is also conformally equivalent to R3, this implies this funny inequality. By the way, I forgot an I and I forgot absolute values around it, but this is essentially the inequality which is equivalent to this one here, which I showed you here, to this inequality here, right? This result. This result you can get out from Hiyase's result, but you know, it's not so clear, right? Because what you have to do is what you have to show, first of all, that an optimizer exists for this inequality, right? And then that this optimizer satisfies this variational equation, etc. That's somewhat tricky. But anyhow, I just wanted to show this, that this is not something which comes out of the blue. This is something which comes from differential geometry. The problem why this argument is not quite up to snuff is the following. The phi could actually vanish, right? The phi which you have in here. So this kind of formulations don't quite work out. Presumably one can actually fix this. Then the other problem is that in differential geometry, you always work in the smooth category of things, which of course we don't do that. And in many ways, I would say the main, what shall I say, achievement is maybe too much to say, but that we managed to carry over these estimates, if you like, simply by differentiating Sobolev functions instead of using C-infinity functions, okay? So I hope I didn't confuse you too much with this kind of stuff, and I thank you very much for your attention.
Thank you very much, Michael, for the nice talk. Is there any question from the audience? So maybe I have one, but perhaps you explained it and I missed it. But so why do you expect the Lossiau function somehow, this function you showed us before, to be an optimizer for the inequality? You at some point you mentioned that you suspect that to be true, but
yeah, we suspect it. You see, I mean, there are too many miracles happening, right? Yeah. I mean, one thing, I mean, it was this. It's kind of. Let me go back, right? When you look. Yeah. So remember, you had this nice diamagnetic inequality, and you sort of think, well, that's the end of the story. Well, you can still improve. And the funny thing is that somehow the modulus to the power 1/2 has to do with the Sobolev inequality, right? So you see, there are too many accidents happening. These things are very all closely related. Yeah. Okay. Mm-hmm. By the way, let me also point out, when you go back to this inequality in where is it? This one. Yeah. Remember, I told you that this is true, right? This equation holds. Mm-hmm. Yeah, for the spinor. Now, you see, once you have this equation, you can actually easily cook up a magnetic field, which produces a zero mode. Well, how do you do it? You take psi, sigma psi, divided by the length of psi squared. That's a vector, okay? Mm-hmm. Now you take this vector and you dot it into sigma, okay? So that's a matrix, right? The psi itself is an eigenvector of this matrix with eigenvalue 1. That's a check. This is standard with the sigma matrices. So now when you take, in other words, when you take 3 divided by 1 plus I squared, x squared, psi sigma psi divided by the length of psi squared, and you declare this your A field. Mm-hmm. That produces you precisely zero mode. And this is precisely the A field, which Yao and I found 35 years ago. Where was it? Yeah, here, this one. It's precisely that. Mm-hmm. So in some sense, we just try to understand how all these things sort of fit together in a clearer way. And certainly we are not done yet. I mean, so what I think we can prove is the following, that if you have a zero mode, then the 3 norm of A is bigger than a certain constant, and this constant is sharp. And you have equality precisely when you have such kind of zero modes.
Mm-hmm.
Yeah. Of course, that's not a statement about the magnetic field, right? This is a statement about a certain particular A field in a particular gauge, right? Mm-hmm. So we have some evidence going in that direction why this should be true.
Mm-hmm. Okay, thanks.
I have a question.
Yes, please, go ahead.
So, have you thought about using these ideas also for the multi-particle case and improve, for example, the stability of matter with magnetic fields?
Oh yeah, right. I mean, there is that. Let's go back. Yeah, now that's a very good point. So remember, I said to you, I told you that here. Yeah, right. So what is the Z, right? I mean, the Z shouldn't be too big. Okay. So then what you could say, well, okay, so what would be a bound on Z? I simply take the field energy, I divide by the Coulomb energy, and I take, if you like, the, what is it? The infimum over all zero modes, right? Yes. That would give you, in some sense, a critical Z. And it turns out this critical Z, Elliot and I, we worked this out, we estimated it about 17,000, right? So this means fortunately, right? And when you take the zero modes, you get about, I don't know, remember, a much bigger number. But with these things, with these kind of considerations, we were able to improve this constant, and we got about now 30,000. Mm-hmm. So the critical Z now is that the estimate is better, right?
Okay. Thanks.
Yeah, that's right. That's a good question. Yeah, exactly.
Other questions or comments? Yes, Gianmichele?
So you introduced this projection, right? Pi.
Yeah.
And so it acts on a tensor product space of a spin 1/2 and a spin 1.
Yeah, right.
Right. And,
yeah,
and
right.
It appears to be invariant on the rotations. So it should project onto one of the reducible representation which comes out. So 1/2 and 1 gives 1/2 and 3/2.
Yeah, right.
On which of the two does it project?
I haven't thought about it. It's a very good remark, Gianmichele. I know it. Okay, well, you see, you really have an excellent education from the APR, which I forgot. I didn't think about it. It's a very good point. I think we should look at this. Yeah, right. Thank you. No, I haven't thought about it, but you're right. It's invariant on the rotations, right? Yeah. Mm-hmm. Yep. Yeah.
Other questions or comments?
Could I ask a brief question?
Please.
So you talked about this motivation for the stability of hydrogen atom in 3 dimensions, and then you also have these results for other dimensions.
Yes.
Is the motivation somehow also extendable to these other dimensions, or could you think of also other?
Yeah. Well, honestly, I don't know. I doubt it. I mean, these zero modes which Yao and I found, they were actually generalized to higher dimension, to higher odd dimension by 2 physicists. I forgot the name of the 2. But I don't think they had any kind of applications in this direction. I mean, physics is in some, well, okay. For me, still in 3 dimensions, right? Yeah. So I don't know. I mean, there is, of course, another reason why you're interested in zero modes. Again, this is now sort of beyond my expertise, but what people do, I think, in quantum field theory, they compute functional determinants, right? And functional determinants usually give you determinants of certain Dirac operators. And these Dirac operators, these determinants show up in the denominator. Now, it's kind of unpleasant when suddenly 0 shows up. That's sort of, so you have to really analyze these determinants, and that's where the zero modes come up, right? So potentially there are certainly other applications.
Thank you.
Thank you.
But does it mean that there are no zero modes in even dimensions?
No, I don't think so. But you know, I don't have an example. So in 2 dimension you have, of course, right? So there is this famous, what is it called, a Aharonov-Kasher result, right? Where you actually can, it's like an index theorem. You can work out this whole thing in great detail, right? And I'm sure in 4 dimension also, but I'm sort of too, I don't know, wedded to 3 dimensions. And we had examples in odd dimensions, right? Which we were able to, which were similar to the ones of which Yao and I found. Yeah.
Other questions? Doesn't seem to be the case. So thank you very much, Michael, again for the very nice talk.
Thank you very much for your